Hey everyone, and welcome. Today we're going to talk about one of the most fundamental ideas that powers, well, pretty much everything in our modern world, quantization. We're going to see how a wild discovery in quantum physics ended up right inside your phone. And just a heads up, this entire explainer is based on a really fantastic lecture by Associate Professor Dr. Jagat Deswaran Ranjan Nen from University Science Malaysia. All right, let's get into it.
It kind of sounds like the setup for a really nerdy joke, right? What could possibly connect the world-changing theories of physicists from over 100 years ago with the device that's probably in your hand right now? Well, the answer is a single, incredibly powerful idea that bridges two completely different worlds. So to find that connection, we've got to start with a really basic challenge. The world that we live in, the sound of my voice, the warmth of the sun, the color of a sunset, all of that is analog. But our computers, our phones, they live in a digital world. So the big question is, how do you translate one language into the other?
This is the perfect analogy for the problem. Think of the analog world as a perfectly smooth ramp. You can stand at any point along its length, right down to an infinite number of tiny fractions. It's totally continuous. The digital world, on the other hand, is a staircase. You can only be on step 1 or step 2 or step 3. There's absolutely nothing in between. It's all made of separate, discrete values. So the challenge is, how do you map that beautifully smooth ramp onto a kind of clunky staircase? Now, this solution, and you're not going to believe this, didn't come from some engineer trying to build a better computer. Nope. It came from physicists who were trying to understand the very fabric of reality itself. Let's jump in a time machine. Back in 1900, a physicist named Max Planck was studying energy, and he found something that just blew everyone's mind. Energy wasn't a continuous flow, like water from a hose. It was shot out in tiny, specific packets. He called them quanta. Then, just 5 years later, a young Albert Einstein took that idea and ran with it, saying that light itself isn't a smooth wave, but is actually made of individual particles, which we now call photons. And the big takeaway from all their work was this absolutely stunning revelation. At its most fundamental, smallest level, the universe isn't a smooth ramp. It's a staircase. Nature, it turns out, is discrete. And that brings us to this core idea, quanta. A quantum is simply the smallest possible piece of something. You can't have half a quantum of energy, just like you can't stand on half a stair step. It is the fundamental, indivisible building block of reality. So just keep that idea of packets or steps locked in your mind. So, this deeply profound discovery about the universe gave engineers the perfect mental tool they needed to solve that analog to digital problem. I mean, if nature uses discrete packets to build reality, well, maybe we can too. And this is where the hero of our story comes in, the analog to digital converter, or ADC. Its whole job is to take that smooth analog ramp of reality and force it into a digital staircase approximation. And this process, this act of forcing a continuous signal into a set of discrete levels, has a name that's taken directly from physics, quantization. So how does it actually do it? Well, an ADC basically repeats 3 simple steps over and over again at lightning speed. First, it samples the signal. It's like taking a whole bunch of super fast snapshots. Second, it quantizes. For every snapshot, it looks at the value and decides which stair step or predefined level it's closest to. And finally, it encodes that step with a unique digital number, usually binary. Sample, quantize, encode. It just does that over and over, billions of times a second. And this just shows you the end result perfectly. You've got the original, smooth analog wave, like the sound of my voice, and then you have the digital version, a series of steps that follows that original shape pretty darn closely. It's not a perfect match, but it's an incredibly good copy. Now, I said not perfect, and that's actually a really, really important point. This whole translation from the smooth analog world to the blocky digital world of steps, well, it comes with a cost. It's unavoidable. And that cost is called quantization error. Just think about it for a second. When the ADC forces a signal's value to the nearest step, there's almost always a tiny little gap between the real value and the step's value. It's basically a rounding error, happening over and over and over again for every single sample. And all those tiny little rounding errors, they don't just vanish. When you add them all together, they actually create a brand new, unwanted background signal. We call this quantization noise. It's that faint hiss or static you might hear on a low-quality digital recording. It's kind of like the ghost of all the information that got lost in translation. So how do engineers fight this noise? Simple. They make the staircase better by adding way more steps and making each step much, much smaller. The quality of this whole process is measured by something called the signal-to-noise ratio, or SNR. Now, don't worry about the math here, just look at the letter N. That N stands for the number of bits the converter uses. And here's the really cool part. For every single bit you add, you essentially double the number of steps on your staircase. This makes the digital copy way, way closer to the original. And it crushes that background hiss. And this all comes together on the tiny little silicon chips, often made using CMOS technology, that are inside all of our devices. The goal for the engineers designing these things is always to get a more faithful copy. It's a constant battle to increase that signal and reduce that noise. They do it by adding more bits, which is exactly why a modern 24-bit audio file sounds so much richer and cleaner than an old 16-bit one. It's all about making that digital staircase as close a match to the original analog ramp as humanly possible. Okay, so we've journeyed from quantum physics all the way to modern chip design. Let's zoom back out now and think about what this really means for all of us. I mean, this isn't some abstract theory we're talking about. This process of sampling and quantizing is happening right now, constantly, inside almost every piece of tech you own. The microphone capturing my voice, the camera recording this, the Wi-Fi signal beaming it to you. It all depends on this unbelievably fast translation from the analog world to the digital one. So, what are the big takeaways here? First, the real world is a smooth ramp. The digital world is a staircase. Second, the key to bridging that gap came from a discovery about how the universe itself works, this idea of quanta. And that inspired the engineering process we call quantization, which creates every digital photo and sound we've ever experienced. And finally, every single one of those digital files is a brilliant but fundamentally imperfect copy of reality. And that really leaves us with a final thought to chew on. We've built our entire information age on this process of making tiny, imperfect copies of the world around us. And it's incredibly powerful, but it's worth asking. In this constant translation from the smooth ramp of reality to the discrete staircase of data, what subtle details, what infinite nuances might we be losing along the way?